let's apply what we've learned in the last video to design an active low-pass Butterworth filter. In this example, we're tasked with designing a fourth-order active low-pass Butterworth filter with a cutoff frequency of 100 Hz. That means that this particular filter should pass all of the low frequencies, 100 Hz or below, and then block all of the higher frequencies. Because the problem asks for a fourth-order filter, we're going to need two Sallen Key sections in order to give us the appropriate filter. Because we have four poles working together, all of the resistors R and all of the capacitors C are going to have the same value. However, the gain K in these two circuits is not going to be the same. In other words, the K for the first section is going to end up being different than the K for the second section. But all of the other values that are labeled the same will be the same. Let's pull up the design procedure that we came up with in the last video. So the design procedure is as follows. First, we're going to choose a capacitor, C, and then use the formula in order to find R. So there's some design freedom here, and we need to have some intuition about what capacitor would be appropriate to choose here. I'm going to suggest using a fairly large capacitor, and the reason for that is because our corner frequency is fairly low. 100 Hz is in the audio range, and it's a fairly low audio signal. That means we're going to need a fairly large capacitor, but I don't want to make the capacitor too large. I don't want to, say, choose a capacitor in the microfarad range, because then that capacitor might end up being electrolytic, and I generally want to avoid using electrolytic capacitors to do signal filtering. Normally, we only use electrolytic capacitors to block DC signals. So with that in mind, I'm just going to arbitrarily choose a capacitor of 100 nanofarads. We now need to calculate R. So the formula can be rearranged. Our F sub B is 100 Hz, and we've chosen C, so R is completely determined. In this example, R comes out to be 15.92 kilo ohms. You're not going to be able to buy a 15.92 kilo ohm resistor, so it would make sense to choose a standard 15.8 kilo ohm 1% tolerance resistor, for example. All of the resistors R then have the same value. I know that the 15.8 kilo ohm value is a good choice because it's in the kilo ohm range. We want the resistors for standard op-amps to come out in the kilo ohm range for the following reason. If we choose a resistor that's too large, say something in the tens of mega ohms range, then that resistor starts to look a lot like the input impedance to the op-amps. And once you have parasitic resistances resembling the actual resistances in your circuit, it's a recipe for disaster. Your filter won't behave as you expect. On the other hand, if you choose resistors that are too small, then the capacitors end up being too large and the electrolytic capacitors aren't as accurate. Also, small resistors end up using more current, so the amplifier works a little bit harder than it otherwise would have to. Something in the kilo ohm range is a good compromise between these two extremes. And with the choice of 100 nanofarad for the capacitors, we ended up with a nice value for R. The second step in the design procedure is to determine the K based on the filter order. This problem called for a fourth order filter, so the table tells us what the K values should be. Thus, I know that the K, or the DC gain, for the first filter segment should be 1.152, and K for the second Sallen Key segment should be 2.235. So the overall gain for the circuit is given by these two Ks multiplied by one another. That is 1.152 times 2.235, giving us 2.575. The third step in the design procedure is to choose any reasonable feedback resistance R sub F. Because I want values to be in the kilo ohm range, I'll pick 10 kilo ohms arbitrarily for my feedback resistor for both Sallen Key segments. Because I know what K is in each segment, I can then calculate what the other feedback resistor should be. We've now calculated every element in the entire circuit. What would the Bode magnitude plot for this filter look like? Let's go ahead and draw it. That is, I want to plot the gain versus the frequency. Because it's a low-pass filter, I know that I'm going to pass all of the low frequencies and I'm going to block all of the high frequencies. I know that right at the corner frequency, which in this filter was designed to be 100 Hertz, we're going to have this transition. And I'm plotting it like this because I've decided to plot H on a logarithmic scale. So we can ignore the little flat line that I just drew. So if I want to know what that is on a log scale, I know that this point is 8.2 decibels. And I know that 100 hertz is my 3 dB point, so we have approximately 3 decibels at this point. And then we know that we have a 20 decibels per decade roll-off per pole. So this is a 4-pole filter, meaning we should have 80 decibels per decade roll off in the filter. So if this is 100 hertz, if I go out to 1 kilohertz, I know that I should be approximately 80 decibels down from 8.2 decibels.